Yeah, I will. I will for sure. No, no, no. I get it. Yeah. Yes. Yeah.
Um, Good morning, all of you. My name is Rohit. I'll welcome you on a 93rd Colloquium of Dr. So, today we have a talk on a title topic atmospheric aerosol chemistry, climate, and air quality. So, today we have a speaker with us, Dr. Professor Douglas Worsnop from Aerodyne Research, USA. So, Dr. Professor, I'll introduce about Dr. Professor Douglas. So, he is a leading atmospheric chemist known for transforming aerosol science through development and advanced aerosol mass spectrometry technique. So, as a vice president of Aerodyne Research and professor at University of Helsinki, he played a major role in advancing in an understanding of aerosol chemistry, cloud interaction, and air quality. Its most influential contribution in the development of aerosol mass spectrometer, that is the breakthrough instrument that enables real-time size-resolved measurement of submicron aerosol chemical compositions. So this technology revolutionized atmospheric observation by allowing a detailed characterization of organic sulfate, nitrate, ammonium in the laboratory, ground-based observations, mobile observation, as well as airborne studies. So over his career, he has contributed more than 800 publications and accumulated over 1 lakh citations, reflecting his profound impact on atmospheric science. Also, he has significantly involved in improved knowledge about SOE, secondary organic aerosols, for new particle formations, aerosol aging, cloud condensation nuclei processes. So, all of which are critical for understanding climate forcing and air pollution. So his study demonstrated how highly oxygenated organic molecular drives particle growth from nanometer size to cloud active particles, linking biogenic emissions to aerosol cloud interactions. So his work has also influenced global climate assessment, including those of IPCC, and supported air quality regulations by improving the particulate matter source apportionment. At last, but he is recently being elected as a fellow of American Engineering Society. With that short introduction, I invite Dr. Professor Dog to start his session. Welcome.
Uh, well, thank you very much. It's a pleasure to be back here again. Um, uh, and this is my title page, and this title page serves multiple purposes. First, as you just heard, I've been at Aerodyne Research, now a senior vice president for over 40 years. And then about 20 years ago, I also became a visiting part-time, but permanent visiting professor at the University of Helsinki. And then also, about 20 years ago, I started spending a lot of time in China. So that now I have active collaborations with all these universities and groups in China. Now, the real point of this slide is that as you can see, I've collaborated actively. I have and still collaborate actively with many universities around the world. So everything I'm going to show is actually due to the work of a whole bunch of people at all these institutions. And I also like to say that there's some competition to, especially in China recently, to get your name on this list. Okay? And the way you get the name, I add a name to this list, is when we co-publish a paper together. And in this context, IITM here in Pune is the only institute in India on this list. And that's actually why I am here today, combined with the fact that you just acquired some new instrumentation. I'm going to talk about mass spectrometry, applied atmospheric mass spectrometry from 1 nanometer to 1 micron. 1 nanometer is a molecule, a big molecule, molecular cluster. 1 micron is an aerosol particle. And finally, I just need to emphasize that, as I said, I have been at Aerodyne Research. We build and supply, support all these mass spectrometers. What I like to say about Aerodyne, it was not an instrumentation company, we're a research company. We're really here to support the research. And that's why I talk about publications so much. It's really about, in the end, it's about publications. And the other thing I wanted to mention, it's really important. Here in India, Tefcorn is our local, what we usually call our local distributor. What I want to say, I think many of you know this, they're our partner in India. So I'm beginning to call them the best distributor we have, because they're actually around the world. Because they're actually get involved in the research supporting all of you. So I will just mention that. Okay. This is my introductory slide to air pollution. This is a picture from Pittsburgh, Pennsylvania, in the eastern United States from 2001. This is the Pittsburgh Air Quality Study, which was the second EPA, big EPA super site project. And these are two pictures of a clean day and a polluted day from Pittsburgh in 2001. When you ever see pictures like this, it's very important to know this number. The camera, the photographer, was 10 kilometers away from that skyline. This is a polluted day, PM 2.5 was 45 microgram per cubic meter. This is not a highly polluted day, but still not a clean day. The point is, when you see these pictures, when this gets up to 500 microgram per cubic meter, to pick a number, then this picture, you see this picture at 500 meters or a kilometer. I mean, this haze. So you always need to know this number if you see these pictures. I just emphasize that. Now, this is significant because on this day in 2001, the EPA daily standard for PM 2.5 was 65 microgram per cubic meter, which means, according to the EPA, then this was a clean day. 2 years after this, that standard was reduced, daily standard, to 35 microgram per cubic meter, which it still is. Now the annual standard is 12 microgram per cubic meter. To put that in perspective, when I first went to China over 20 years ago, there was no standard. And then they put in a standard of 100, and then they lowered it to 65. And now this year, they are proposing to lower it to 25 microgram per cubic meter. And that reflects the fact that just like the United States and Europe, they are now finally or gradually improving their air quality. And as part of that, you have new standards. Now, the real point about another perspective on this picture is on this day or days like this, if you took a satellite picture over the eastern United States, where Pittsburgh is about here, you'd see that when the air looked like this in Pittsburgh, it was actually typically a regional event in the eastern United States. And often, the meteorology was such that that haze was actually advected over the Atlantic Ocean. Now, this is actually very important. This is the largest aerosol direct effect there is. When you put that haze over this dark ocean, that's a radiative forcing of tens of watts per square meter. Okay? And what's important is this haze evolved in the United States, the eastern United States, after the industrialization and the economic development of World War II. And so as our CO2 emissions increased in that same time period, we also increased this haze. And this is a direct global cooling. And now that we have cleaned it up, and now the point is, this never happens in the Eastern United States anymore. We simply do not have haze events anywhere near this intense because the EPA successfully cleaned up the air. This is if you're a climate change person, this is a real problem. Okay? Well, what happened in the same time period we really cleaned this up, the Chinese totally polluted their air. So there are satellite pictures just like this over the Pacific. The outflow from China and East Asia over the Pacific Ocean. And now so the Chinese, East Asia compensated, but now they're cleaning up the extreme haze. So you know who's next? We're here in India. You now have the reputation of having the worst haze, the worst polluted sometime of the year in the world. And you know what you're doing? You're also blowing this haze over the Indian Ocean. Okay? My point is, and we all want, but you want to clean up the air for obvious reasons. It's bad for health. Nobody likes to look at it. But my point is it's really connected to climate change. And I'm going to say a little bit more, and then I'm going to stop, because I'm really going to talk about the chemistry. My talk is about the chemistry of this haze. So one more slide, one more tutorial to put this all in perspective. This is now a budget of an energy budget of the planet Earth from an IPCC report. But the key number here, the first number, is that the total incoming solar radiation is 340 watts per square meter. The second number is that about 77, about a quarter of that is directly reflected by aerosols and clouds, which means this energy, a quarter of this energy never gets to the surface of the Earth. Now, the CO2 forcing for 100 ppm of CO2, added CO2, is roughly 2 or 3 watts per square meter. That's just a number. Now, that number is roughly 1% of that number, or the net number, okay? 1% of 278 K, which is the temperature of the Earth, is 3 degrees C. That's called global warming. 100 ppm of CO2 will increase the temperature of the Earth by 3 degrees C, because it's a change of 1%, a trapping of 1% of the sun's energy. Now, to put that in perspective, that same 2 or 3 watts per square meter represents 3% of that number. If we change the aerosols and clouds by 3%, the total radius scattering, that's equivalent of an added CO2 concentration of 100 part per million. There are 2 points. We cannot measure this number to that accuracy. Okay? That actually may be changing because the next generation of the satellites, the coming generation, maybe it's already been launched. But one of the things, we are now going to measure that number much better in the future. We're going to try to measure that number. But the other point is that the anthropogenic change, or the change in aerosol concentration at a global scale that we're talking about for this is in the parts per billion range in terms of molecular concentration. So molecules that decide to condense into aerosols in the part per billion range on a global average have an equivalent impact on the solar radiation budget as CO2. There are another really big difference. We can measure this pretty accurately, and this is a relatively simple problem because the CO2 is homogeneously mixed in the whole atmosphere. The main reason aerosols and clouds are so hard is they're completely inhomogeneous. There is no average aerosol concentration. For sure, we all know that clouds come and go all the time. And that's why this is really hard to measure. And the final point is this number, even this number, this number, this 3-degree change compared to that, is based on, which comes from IPCC calculations, is referencing to the atmosphere in 1750. There is no way we have any idea what this number, the extent of aerosols and clouds in 1750 compared to now. We definitely believe in the polluted, anthropogenically perturbed regions, we have increased the aerosol, and probably we have increased the clouds. But this is why, to end it here, why aerosols, when you're talking about climate change, global warming and climate change, this is why aerosols and clouds will not go away. Because this is how large their impact is. And I'm not going to talk about climate anymore. The rest of my talk is about the chemistry of the aerosol particles, even on a global scale. So I'm a measurement guy. I measure aerosols, in particular aerosol chemistry. I'm not a climate guy, but this introduction is supposed to convince you that if you care about aerosols and climate, we got to understand aerosol chemistry and the aerosol life cycle. And also, and in this place, this institute, we also care, you also care about how those aerosols affect clouds. Okay? And I'm not a cloud guy either. I'm an aerosol chemistry measurement guy. But this is why I maintain that if you care about aerosols and their impact on clouds, the details of where am I going now? Yeah, okay. The details matter. I should get going now. I already said this. The Clean Air Act in 1970 and 72 is the most successful legislation in the history of the United States, if you believe our propaganda. But it's also true. This is now a picture of New York City in the 70s, New York City now. New York City doesn't always look like this, but it sure doesn't look like that anymore, okay? In the 70s, it was total suspended particulate, which turned out to be mostly dust from cement factories and smoke from steel mills and power plants. Then the focus shifted to PM10, and then in 1997, EPA established the first PM 2.5 standard. And this 1997 number is relevant, or the year, because it was exactly in that time period we invented, at Aerodyne, we being John, Jane, and I, invented the aerosol mass spectrometer. And I'm not going to say too much about it. The key point is that it's a differentially pumped molecular beam mass spectrometer with an aerodynamic lens from the University of Minnesota, injects the particles in to this chamber, in the vacuum chamber. We pump away all the air. We deliver all the particles to the detector. In the end, this is a particle concentrator. We inject all the particles from atmospheric pressure. This is sampling direct from atmospheric pressure. And only 1 in 10 to the 7th of the air molecules gets the aerosols are suspended in air. The particles get to the detector, but only 1 in 10 to the 7th of the air molecules get to the detector. And that's just a particle concentrator. This is the detector. This is in high vacuum, an electron impact ionizer, connected to a positive ion mass spectrometer. The particles hit this tungsten oven. This is 3 millimeters in diameter, heated to 600 degrees C. What we call the non-refractory component of the aerosol, which is everything that vaporizes at 600 degrees C. And that's most everything in the atmosphere, except for dust, oxide particles, or totally refractory at 600 degrees C, or black carbon. We can actually detect black carbon if we add a laser. But the point is, everything, all of the non-refractory, everything that's in the particles that vaporizes, we detect all of it. We use electron impact ionization, which is universal. It's relatively easy to quantify, and it works. Okay? We get a mass spectrum now. This is now the mass spectrum of the aerosol. And it's colored from inorganics and organic. Organic is carbon containing. We know what this is because we know what all these ions are. We can separate the inorganics and organics because of the sulfate fragments, nitrate fragments, ammonia fragments. And then we have all this green, which are ions that contain carbon. And we spend most of our time, actual time, trying to analyze this distribution of carbon fragments. Because the disadvantage of the AMS, or the disadvantage of both heating the particles and then using electron impact ionization, is that we destroy most of the molecular information, much of the molecular information, and particularly for the organics, these are all decomposition products, but the patterns still have a ton of information. And much of the rest of my talk, or much of the work in the last 25 years, is trying to interpret that organic pattern. Now, the final thing I say, looking at this slide, is there are roughly 1,000 people in the world, young people, who know this spectrum by heart. The colors, and they know a lot of these fragments. When I say that, I'm also probably including SIMS, chemical ionization mass spectra. What I say to all the young people in the audience is, if you know this spectrum, you know how to operate the instrument, you know how to analyze these peaks, and eventually know how to interpret those peaks in terms of aerosol chemistry, you are employable. Okay? There are 500 going on 600 in general of these instruments around the world. And every group needs young people. I mean, it's always young people who have to deal with this. Young people to interpret this, okay? And I'm here specifically to help a bunch of you interpret whatever spectrum we have. And this is just the truth, okay? Now I like to tell this story. I created this slide at the Asian Aerosol, I didn't create it, I brought back this slide at the Asian Aerosol Conference in Mumbai last December. When Spiros Pandis, who gave the keynote lecture, talked about the Pittsburgh air quality study and how the AMS, almost in his words, changed everything in terms of how we understood atmospheric chemistry. Now I'm going back to two of those organic markers, M/Z57, which is C4H9 plus, M/Z44, which is CO2 plus. I plotted M/Z57 here and compared it in red to CO. And you see this M/Z57 tracks CO pretty well. It turns out this is a hydrocarbon. It's actually a fragment from lubricating oil that is condensed on diesel soot particles, which the diesel vehicles emit most of the CO, and they emit most of what we call the primary organic. On the other hand, CO2 plus, which is now oxygenated carbon, if you look carefully here, I'm compared in black, the M/Z44 to ozone in purple. You can see a clear diurnal cycle of the CO2 plus in the aerosol, compared and also with ozone. And then you see at this date, the CO2 plus stuff starts drifting up. That's called a haze event. And that's oxidized organic. You see the hydrocarbon organic doesn't show any of that, okay? It gets a little bit dirtier because the air's thin, but you see, that is actually a haze event. And this is direct evidence that the haze, the particulate that increases during a pollution event is photochemical. I mean, sulfate and nitrate also go up, well, sulfate in particular, but and the organic aerosol goes up, but all the organic aerosol that goes up is oxidized. I mean, I'm going to say this is the message of my talk, is the SOA, which is the major component of the organic aerosol, is produced by the same photochemistry that produces ozone. And now I'll skip this over, and we now have we have a higher resolution mass spectrometer. We can resolve the details of the aerosol chemistry better. I come to this famous map that we published in 2009. This is analysis. This is of 40 campaigns measured by 17 institutes using the aerosol mass spectrometer. The aerosol, I used to say this was a global picture of the aerosol, and then I realized it was only the northern hemisphere because we didn't have any measurements in the southern hemisphere. Without going through the details here, I can summarize. I will just mention this article now has close to 4,000 citations or something like that. And to summarize everything, what we show all around the world is that the aerosol, this is actually PM1 aerosol, but the PM2.5, it's roughly half organic, inorganic composition. That really wasn't news. What was news is the oxygen to carbon ratio of the organic was, on average globally, was about 0.7. And that was really high. That was at least twice as high as people thought. And that's the real, that was the real breakthrough with the AMS, is that we can measure the highly oxidized carbon, get a measure of it, the total. And that was new, and we're still talking about that. I also like to say that the cleanest site in this picture was the Hutila Boreal Forest Station in Finland, and then Beijing in China. And since we published this, I spent most of my time either in Hutila in Finland or in Beijing or other megacities in China. The final thing about this plot is this legend, which is about the O to C, is on top of India. And the reason it's on top of India is we didn't have any measurements in India in 2009. And on this map now, at least in the winter, India has the record for the highest loading. And that's related to why I'm here. Okay? To give one more picture, in 2005, we drove our mobile laboratory to this mountain, which is overlooking Mexico City. Mexico City is a mega city of 20 or 25 million people. It's really special. In the context, it's on a plateau. Above everything, there's nothing much around it. And when the air is coming from the right direction in the morning, it can be really clean. The ozone is low, and the OOA, secondary organic aerosol, is low. And then in one day, we watch the haze form and come up to us on top of this mountain. And you see both the ozone and the SOA, organic aerosol, increase. There are very few places where you can see a picture like this from very low in both of them to go high in one day. You see local correlations of OOA and ozone, but never from very clean to pretty polluted in one day. And this is what, again, a direct observation that the OOA is being formed by the same process that's making the ozone, the same photochemistry. There's even here, this is a biomass burning plume. There was actually a fire over here. I mean, not a fire, there was some refuse or trash burning over there. We know what fire this was. And this is actually interesting because we could separate in the mass spectrum the BBOA. But in this particular plume, there was no ozone formation. This is still a big deal. Some forest fires, so biomass burning, produce ozone, and some don't. It depends on the details of the chemistry, but this is still a hot topic of debate. But this was a direct observation of this place. In this case, the biomass burning was not coupled to the ozone formation or coupled to ozone formation. To summarize everything I just said, the big issue used to be how much of the particulate, how much of the aerosol is primary. I mean, that is aerosol directly emitted from the earth, almost all through combustion of one sort or another, and somewhat how much of it is secondary. It produced from vapor emission and then gets oxidized to molecules, organic molecules that condense into the aerosol. This is really also true for SO2, for sulfate, SO2 going to sulfate, NOx going to nitrate, and it's all coupled to the process to make ozone. And finally, just to give the number, for these gases or organic meshes, either biogenic VOCs or anthropogenic VOCs, overall the yield of this gas phase oxidation to make molecules that condense into aerosols is about 5 or 10%. All of the organics in our oxidizing atmosphere get oxidized, and they interact with those OVOCs make peroxy radicals that interact with NOx to make ozone, and 5 or 10% of the peroxy radicals of the organic oxidation ends up in the aerosol. To say all this all over again, this is a schematic of the natural aerosol budget life cycle, where condensable molecules can make molecular clusters, nanoparticles that become CCN. What I just told you is that the CCN, the larger fine particles, are mostly oxidized. What did they do? Oh, here we go. Oxidized SOA or N-sulfate. If you're near a city or an urban area with urban emissions, you see a lot of ammonium nitrate. And this is exactly the point at which I was recruited to go to the University of Helsinki. As many people may know, in the University of Helsinki, there's only one part of this cycle that's important. That's called the nucleation and new particle formation. I was literally recruited to Helsinki to measure the chemical composition of these clusters that lead to nanoparticles. But the point I like to make is these molecules, these condensable, really low volatility molecules that sometimes can make clusters. Actually, all of these, almost all, 99.9% of these molecules actually condense on the condensation sink. So when you're studying this, you're also studying that. So, so when I went to Helsinki, we invented the chemical ionization mass spectrometer. I'm not going to explain it. The version I like the most is you add nitrate, nitric acid to make nitrate ions, nitric acid here, that we interact, again, at atmospheric pressure. The ions that are sampled into the time of flight mass spectrometer. I should always mention that almost all the mass spectrometry, in the chemical ionization mass spectrometry, I copied or replicated everything Fred Isley did at Georgia Tech and NCAR. All we did was introduce a time of flight mass spectrometer that has up to 1,000 times more sensitivity. We took this thing to Huhtala in Finland, and the first day, this is the data from the first day and the first night. And the first day, we saw sulfuric acid clusters. The appearance of these sulfuric acid clusters at 10 and 11 in the morning corresponded exactly to the appearance of new nanoparticles, so that sulfuric acid and ammonia were dominating nucleation in Huhtala, which is exactly what we expected. But then at night, we saw a completely different spectrum. I'm not going to try to explain this, except to note that we detected this ion that turns out to be this ion, C10, H1409 clustered with a nitrate anion. And that's the basis of nitrate chemical ionization. But most important, we detected all these large carbon-containing organic ions. And this is C10H1409. The major VOC in Huhtala in the springtime, when this was measured, is a terpene, alpha-pinene, C10H16. This was amazing. It appears that we took C10H16 in the gas phase and added 9 oxygens to it. This is a gas phase observation. Okay? This should condense into the aerosol. To make a long story short, Mikhail N., who was one of my students in Helsinki, went to Jülich to work with Thomas Mento in their plant chamber, mixed ozone plus alpha-pinene, created that spectrum in the lab, almost identical to the nitrogen spectrum in Huhtala. We discovered LVOC, extreme low volatility organics. We now call them highly oxygenated organic molecules. Most important thing, we saw C10 and C20 molecules with very high O to C in the gas phase. This is a major source of that extra O to C that the AMS measures. It turns out it's auto-oxidation. I'm not going to try to explain it, except that we now understand that we can add 3, 4, 5 oxygen molecules to a terpene C10H16 backbone in seconds. It turns out NO with nitrogen oxide, NO levels are really important in Huhtala. NO, NOx levels are relatively low. So we favor this process. But to summarize everything I've just said, this is a schematic of how you go from 1 nanometer particles to 100 nanometer CCN particles. You need, in the northern hemisphere, where there's a lot of SO2 and a lot of ammonia, you need sulfuric acid in the base to form new particles. But the important new thing is that all the growth, so almost all the growth, from nanoparticles to CCN, where if we're an aerosol cloud climate aerosol cloud person, what we care about are the CCM. But the organics do all the growth. I mean, all the growth from sub 10 nanometer to 100 nanometer, almost everywhere in the atmosphere, except if you're in a power plant plume or in a really polluted region, is done by organics. And that was a new story. NOx is really important in this chemistry. If you go to China or come here, there's a ton of FVOC that make haze. Once you have these particles in, there's a whole ton of semi-volatile organics that can grow them to make haze. If you're here or in many places, biomass burning, direct injection of both particles and vapors is really important. But this is the aerosol budget, okay? And my main thesis is if we want to understand atmospheric aerosols locally, regionally, globally, we have to understand this chemistry. And these organics, this green part, is thousands of molecules. It's just, this is what the AMS was able to detect. And now with the SIMS, we're trying to detect more and more of those molecules. I'm not going to say much more about that, but it's that complexity that we are trying to resolve, from local, regional air pollution, air quality, to how it impacts the climate or the planet. So to shift the story, I'm going to go to China. This is the cover of Science magazine, 2 weeks before the Summer Olympics in Beijing in 2008. And the subject of this article was really simple. Is Beijing going to look like this during the Olympics? And the Chinese knew all about this. And it turns out that they bought the second, but the second AMS, the first time of flight mass spectrometer in China, was sent to China in the summer before this. We operated it for 12 weeks before, during, and after the Olympics to measure what the aerosol looked like. Okay? Now, it turned out that the air in Beijing didn't look like that during the Olympics. And this next slide explains why. And it's been where this is actually data we measured in 2006 in Beijing at CAMS, the Chinese Academy of Meteorological Science, which is part of the CMA, Junyan Sun's group. And what's plotted here are 5 pie charts, and 3-day back trajectories associated with those pie charts. What this says is when the air comes from the north, is when the aerosol loading in Beijing is low. And in contrast, when the air comes from the south, and when these back trajectories get short, and a short 3-day back trajectory means you have stagnant air. And so when you get stagnant air, and the air comes from the south, you get the highest pollution. This particular one, there used to be a really big, dirty power plant out here, which is now gone. But the haze, what's important here is this is Hebei province, right here, just south of Beijing. Hebei province is the most industrialized province in China. And so when the air gets stagnant and it comes from that province, that's when you get extreme haze in Beijing. Now during the Olympics, 3 things happened. They got unseasonably a lot of air from the north. It also rained a lot during the 2 or 3 weeks of the Olympics. And finally, they shut down this whole province for 2 to 4 weeks. They shut down every factory, all construction and restricted traffic a lot. And it helped. Okay? This was the first experiment at this scale ever done, atmospheric experiment. And you know what? The Chinese were happy. They were optimistic. They understood the air quality and how to clean it up. There was only one huge problem with that optimism. First, they got lucky. The meteorology was favorable. But most important, you can't shut down Hebei province. This was a one-time event. They've actually repeated this experiment for big international meetings in Shanghai, Guangzhou, Beijing. They have never done the same experiment where they shut down everything. Okay? But what happened? From 2008 to 2013, the haze in Beijing got twice as bad. And finally, in 2015, they put some money where the mouth is. So, I mean, this is a random plot. It's not really a particularly accurate one. But until 2015, the aerosol was just going up. But then starting in 2015, the aerosol got reduced by over half. I mean, these numbers don't mean much. They're not accurate. So that they cut the aerosol. This is nominally the average aerosol in Beijing from 100 to 50 micrograms per cubic meter. They actually have done a little bit better. They have a separate problem is that during that time period, ozone went up. Didn't go up this much. It went up 10 or 20%. And this is because they cut SO2. They started to try to get industry to clean up emissions. They cut NOx a little bit. But what's most important here is they managed to do this in 10 years. Okay? And they're only halfway. And since then, in the last 3 years, this has mostly stopped. It's still drifting down, but they have stopped improving it because they've taken their foot off the accelerator. Now, I mentioned the United States. We did the same thing, but it took 40 years. And one of the reasons the Chinese did it faster is first, they had in their top-down economy government, they established policies, relatively extreme policies, and they could do it quickly. But on the other hand, they took advantage of all our experience. So they knew what to do much better. This is now a picture from Delhi last November, okay? I was at the Asian Aerosol Conference in Mumbai 2 weeks after this picture was taken. The reason the Asian Aerosol Conference was held in Mumbai is they were worried the air would be too dirty in Delhi, okay? And it was. But it turns out Mumbai, during the week of the Asian Aerosol Conference, when we have all these aerosol scientists there, they do something. Had the worst week ever in Mumbai for air quality. I mean, Delhi was 200 microgram per cubic meter. Mumbai was 100 microgram per cubic meter. So this is 2025. My question to all of you is how long is it going to take India to improve this? Understanding that the air, as far as I understand it, overall the air is becoming worse every year, okay? And it's continued to become, my point is going to continue to become worse until, as a government, a society, a people, you decide to do something about it. It's what happens when you have more people, and more economy. At some point, you cross a threshold where the emissions and the chemistry, and because realize we live in an oxidizing atmosphere. Everything we emit gets chewed up by the sun. Okay? And it's just going to get worse until you proactively start going after the emissions. And the tiniest thing, and then the economy, and this is the point. The Economist published this pile on, pointed out in February of this year that the air is getting so dirty that's going to hurt your economy, hurt the growth. I mean, people like me don't like to come, especially don't like to bring our families or investors spend time when the air is this dirty. This happened in China. I'm telling you, in the teens, 2010 to 2013, China had the same crisis, and a similar crisis. And then, okay, just one second. And then I finally wanted to say, at this point, and I won't say it's by coincidence, but during the last 20 or 25 years, the Chinese acquired roughly 200 of our mass spectrometers, okay? I am not saying our mass spectrometers solved the problem, but they contributed to the measurements and the understanding of the chemistry that led to improvements. And now I wanted to show this slide, because this is why, really why, I am here in Pune. Now, in 2018 or 19, I think 2018, I visited Pune because you had just acquired a mass spectrometer. I don't really remember exactly. And somehow I met Professor Tara. And the two of us, within 10 or 15 minutes, dreamed of putting what we call a mini AMS on the airplanes in Kaipex. And we put a mini AMS on the chase plane when the first plane was seeding the clouds. And this is just an example of a flight track. You seeded the cloud, and then the plane flew downwind and saw the cloud form. Now, actually, the mini AMS worked really well. We measured cloud residuals fairly. Every time the chase plane flew through a cloud, we got a cloud residual signature. And on one special day, specifically flight, there was a cloud seeding, and then the circles are actually vertical profiles of the chase plane going up, going at high altitude, in the cloud that formed here. So that shift over here, we have the number of cloud residuals versus altitude, where the cloud seeding happened down here at the base of the cloud, and then over the next half hour or hour went up. We saw potassium and chloride in the cloud residuals, which is the seeding, the marker of the seed. So we watched the seed particles go upwards in the updraft of the cloud. And to my knowledge, our knowledge, this is the first time this ever worked this well. One flight, one cloud observation does not tell us everything we need to know. But this was a big success, I think, from our point of view. And from my perspective, it's sort of and I was here in 2018. I think these flights were in 2019. And I was supposed to be here in 2020 to come to the cloud physics conference. But this thing called COVID happened, so I didn't come back for a while. But anyway, I'm here now. You guys have acquired some mass spectrometers, and I'm here to help you try to use them to really understand the chemistry. Now, this is my final data. I'm now showing this to people, okay? This is an unnamed city in India. Okay? This is ACSM data of a month or two of ACSM data in this unnamed city. And the secret is, so I have to tell you, we're in this isn't a city, we're in the middle of nowhere right here, where there are three cities nearby, one to the north, one to the east, and one to the south. Now the secret is that this city to the south, for example, it has this huge sulfate plume. These are wind roses in wind speed. So when you see this red blob, that means the sulfate came from that direction and far away. And it turns out that city is Bhopal. And this is that is from Subrata, the ACSM at the new Bhopal site. And I believe this is the paradigm of how to do source apportionment of the aerosols. I mean, there's a lot of details here. This is the inorganics. This is the organics. This is black carbon. And it's complicated. But what's important is that if you look at all these patterns, they're all slightly different. Okay? So we have a BBAO, biomass burning, cooking aerosol, HOA, primary, and then some aged ones. If I now shift the slide so that here, these axes are all different. Here, I've made the axes of these all the same. And you can see we have identified 9 or 10 different types of aerosols. They each come, the 2 types of burning. One comes mostly from this city. One mostly comes from this city. You see that the pure black carbon is actually very low. It's all local. The cooking is local. The HOA is mostly local, and so on. And my point is there's a ton of information in here for this site. I mean, there are 3 cities here that are impacting the air in the city, and it's mostly, and it's dominated by organic. And I believe you analyze this and get more data. I mean, more measurements of other gas phase species. You really can identify where the aerosol is coming from. And if you identify, I mean, there are different, there's trash burning here, I mean, whatever, it's all there. And I think my thesis is really simple. I'm a measurement guy. If you go around India making measurements like this, you will figure out in a local regional basis what's controlling the actual aerosol. And I believe that information is what you need if you're going to most effectively and efficiently try to reduce it. What do I have next? And so to summarize, this is a slide from Markku Kumala, the big professor in Helsinki, where he's contrasting direct emission of particles to airborne production, where the key point, this is equivalent to primary and secondary aerosol. He thinks these are the misleading terms to policymakers, for example, primary and secondary. It's direct emission of particles, and then photochemical oxidation of vapors to make secondary particles, airborne production. The key point of my whole talk is this is much more important than that. Unless you're directly in a city right next to a highway or, a dirty factory, this is not unimportant, but this is much more important. And this is where the regional, even climate effects happen. And the other complication is, especially in India right now, is you have a lot of biomass burning. I shouldn't say biomass burning, just burning. And burning has direct emission, but in fact, I should fix this. This arrow should be smaller than this arrow. there is a lot of direct emission, and especially if you're near the fire, that's important. But actually for the regional effects, the vapors that are part of the biomass burning, that get oxidized, turn out to be more important in terms of the total aerosol. And my message is, if you don't proactively go after all of these sources, it's just going to keep getting worse. It's just the nature of it. I mean, to put it in a different context, this is the evolution of me as a human being, a knowledgeable human being. I grew up here. I spent a lot of time here. But what's really true is that more people live inside this circle than outside of it. And as an air pollution, aerosol chemist, we have fairly successfully cleaned up our air. The Europeans largely true. But this is where the action is, both for the moment for regional air quality, but also for climate change, okay? So I spent a lot of time in this triangle from Shanghai to Xi'an to Beijing. 10% of the population now lives there. You realize that happened in the last 20 years because half of the people, I don't know, half of the people in the provinces moved to that triangle, that northeast triangle, in the last 20 or 30 years. What's important, this also became 10% of the GDP. So, you know, all those people and all that industry, all that economy, for 10 to 15 years, this was the worst air in the world. Okay? We're here now. And I'm going to call the IGP. I think there are roughly the same number of people. And the economy is growing, though it's not 10% of the world's GDP. But the tiniest point, if you have way too much burning, but there's a lot more than just burning going on. So I'm going to stop pontificating. I'm a measurement guy. If you don't measure this carefully and understand it carefully, well, you're not going to be able to make it better or reduce it. And I'm going to stop there. Thank you.
Hello. Thank you, Professor Dan, for enlightening talk on aerosol chemistry. So he showed us or told us the role of aerosol chemistry in the atmospheric processes, importance of atmospheric AMS spectrometry and its measurement over globally, and case study over China. So thank you once again for the enlightening talk. The floor is open for question and session. If you want to have some questions or interaction.
That's good. Thank you. It's a very nice talk. So my question is, when we are talking about the Delhi, so aerosol contributions, secondary aerosols are more major contributions around the 60% than the primary during the winter time. So how we have to do detailed source assessment of secondary aerosols, and as well as how to control the secondary aerosols in the Delhi.
I mean, look, I don't have anything magic to say about that, except that if I take a plot like this is telling me where different types of aerosol, inorganic and organic, are coming from. I mean, the AMS measurements by themselves don't tell you everything you need to know about this aerosol, but they point you in the right direction. So you need to go make measurements here and here to figure out where that aerosol came from, which emissions. But you have to chase down that way. There's no magic. You have to make these sorts of measurements and then measure the sources, model it. My point is, this is the detailed information of the phenomenology of the aerosols, where they come from, how they get how they grow, how they get transported. That is the start of trying to understand how to make it better in the most effective way.
How much confidence about the AMS?
Excuse me?
How much confidence about the detailed identification of SOI from the air?
I have total confidence, but it's not enough information. Like in practice, what we're doing now, I'm doing this in China, doing it in different places. This is the AMS is capable of measuring the total aerosol parameters. Figaro or Easy, or now we have Wally, that can look at the molecular composition of the aerosol of this and try at a molecular level to better identify the composition and potentially the source of that. That's what we're now doing actively in China and the US and Europe. And it's research. But we're learning more and more. And the point is, in India, if you're willing to invest in the instrumentation, but even more so in the people to make the measurements and interpret them, I believe we now can acquire enough chemical information to answer your question. But it's a complex problem. There's no other way to put it.
It was a nice presentation, sir. I have a very basic question. Like these non-refractory components, we can measure these areas,
Yeah.
but these refractory we cannot measure. That's the limitation. This temperature of the vaporizer 600 degrees Celsius. So why don't we just increase the temperature and include the refractory pattern like VCN?
I'm sorry, say that again.
So my question is, why don't the engineers just increase the temperature?
Because it's not practical. You can't heat. You need a plasma to go higher. That's why there are 2 points here. That's why having a black carbon instrument, an ethylometer, is really important. And also, it's now becoming, I'm going to say, standard or more standard, that you also need an instrument to measure metals. The one that I'm most familiar with is called Exact. But the Exact instrument, for example, will measure dust. But dust, from my perspective, dust most of the time isn't that important. When there are situations where it is. But that's why you definitely need black carbon. I'm going to say the standard measure of PM 2.5 chemistry, reference measure, is AMS plus black carbon. And you get most of the aerosol mass that way. But yeah.
No question. Okay, thank you.
You're welcome.